Bismillah, Alhamdulillah, wassalatu wassalamu ala Rasulillah. This is the second part of section 11.1. Uh, we mentioned the definition of the sequence and how to find the first few terms of a sequence, and how to denote the sequence notation, and how to find an for some sequences. Okay, finding an is not an easy matter. For some sequences, you can do like what we did in the previous part, and you find the formula for an. Now we will talk about the limit of a sequence. A sequence can be pictured either by plotting its terms on a number line or by plotting its graph. So for example, here we can plot the sequence on a number line like this. So this sequence, the first term is half, so we plot half. A1 is half. A2 is 2 over 3. So this is A2, A3, A4, and so on. And we notice that this sequence approaches 1 when n increases, when n goes to infinity. Also, if you plot the points of the sequence, the graph like this. So this is the number 1. This is A1, half, A2, A3, A4. A7, for example, is 7 over 8. So you can notice that this sequence is approaching the number 1. So we can say that the limit of this sequence when n goes to infinity is 1. So we write it like this: limit an when n goes to infinity is 1. There is, if you write plot sequence on Google, you will find different sites. You can write the sequence there, and the site will plot it for you, will graph the sequence for you. So the graph will consist of discrete points. 1, when n is 1, I have A1. So 1 with A1, this would be the first point, 1.5 in this case. 2 and 2 over 3, this would be the second point, and so on. See, so these points will give you the graph of the sequence. So limit an, the sequence an is L as n approaches infinity. We write this if the sequence an has the limit L. And if we take n sufficiently large, n 100,000, 10,000, then the terms of the sequence will come very close to L, because L is the limit of the sequence. So for example, here, 4 over 5, if after when n is 10,000, you will have 10,000 over 10,001. So this is very close to 1. When n is million, you have million over million 1. Million and 1. So very, very close to 1. So when you increase n, then the terms of an will become very close to L. This is what we mean by limit an is L. If the limit of the sequence exists, if it has a limit, like this sequence, okay, then we say that the sequence converges. So here we say that the sequence converges to 1. Come closer, come close to 1. So the sequence converges to 1. Otherwise, if the sequence has no limit, then the sequence is divergent, or we say that the sequence diverges. So a sequence diverges if the terms of the sequence do not approach a single number. like the previous sequence, it approaches one single number. So for example, here, this sequence, two numbers, at one number, at two another number, at three number, at four the same number. So for example, 1 and 2. So for some terms it's 1, for other terms it's 2. So the sequence at the end does not approach a single number. So this is a divergent sequence. Or the sequence could go like this to infinity. So it doesn't approach a single number. So it's divergent. It increases like this without bound. The limits, we know the laws of the limits. They work here, of course, because we have a limit when n goes to infinity. So we have the sum law, difference law, constant multiple. The c, you can take the c out of the limit. You can multiply. The limit of product is product of limits, the product law, also the quotient law. Also the limit can, the limit of a to power b is the power of the limit of an. So let us now try to find some sequence limits. So this is a sequence n over n plus 1. What is the limit of the sequence? How to find the limit of a sequence when n goes to infinity? Well, if you remember, when x goes to infinity for functions, we take the highest power over the highest power. So I can say that this is limit n approaches infinity of n over n. The highest power below is n. And n over n is 1. So the limit of 1 when n goes to infinity would be 1. So the limit of this sequence is 1, and this sequence converges to 1, n over n plus 1. Is this sequence convergent or divergent? To find out, I find the limit of this sequence when n goes to infinity. In the numerator, I have only n. In the denominator, I have n plus 10. N is greater than 10 when n goes to infinity. So this is the highest power. But now n over n to the power half is n to the power 1 minus half, which is half. And infinity to the power half is infinity. So the limit of this sequence is infinity. It doesn't approach a number, it goes to infinity. So this sequence is divergent. Some exercises. Determine whether the sequence converges or diverges. If it converges, find the limits. Well, I will find the limit first to find out whether the sequence converges or diverges. Infinity plus 2 is infinity. Square root of infinity is infinity. 5 times infinity is infinity. So the limit is infinity. And this sequence is divergent. Limit an when n goes to infinity. The highest power in the numerator is 4n squared. This is the term with the highest power. The term with the highest power in the denominator is 2n squared. N squared cancels with n squared. 4 over 2 is 2. Limit of 2 when n goes to infinity is 2. So the sequence converges to 2, or it is convergent. Here, limit when n goes to infinity of an would be the highest power in the numerator, the highest term, the term with the highest power. And here 2n. Now 4 divided by 2 is 2. N squared divided by n is n. 2 minus 1 is 1. 2 times, now I replace n by infinity, so 2 times infinity is infinity. So this sequence is divergent. So like this, when you have a limit, it would be convergent. When there is no limit, it would be divergent. So here, the highest power of the term with the highest power. In the numerator, I have only one term. In the denominator, square root of n. Now, square root of n cancels with square root of n, and I will have limit of 3, and it's 3. So this sequence converges to 3, and it is convergent. Sine n. What are the terms of this sequence? It is sine 1, sine 2, sine 3, and so on. Well, what is the graph of sine n? I know the graph of sine x, but the graph of sine n, sine 1, for example, would be somewhere here, then here, like this. It would go like this. It oscillates between 1 and -1. So when n goes to infinity, it would be a number between -1 and 1, but I don't know. It doesn't approach a single number. So this sequence is divergent because it does not approach a single number. It oscillates between 1 and -1. We will have some theorems here to help us in finding the limits of the sequences or to determine whether sequences are convergent or not. The first theorem says if we have a function f of x, and if the limit of the function when x approaches infinity is capital N, and if f of n equals an, so if I replace x with n, I get the nth term of a sequence where n is an integer, okay, 1, 2, 3 to infinity. Then the limit of the sequence is also L. So it simply says that if you have a function like this, the sequence, if f of n equals an, then the sequence are discrete points on the graph of the function. So if the function approaches L, then the sequence also approaches L. So that's easy, and we can use it. It says, what this theorem says, whenever you want to find the limit of a sequence, you can go to the function and find the limit of the function. And whatever limit is there, it would be the limit of the sequence. So for example, to talk about the limit of 1 over n to the power r, we can talk about the limit of 1 over x to the power r, the function 1 over x to the power r. And we have seen that if r is positive, then the limit when x goes to infinity of 1 over x to the power r would be 1 over infinity to the power r. R is positive, so it would be 1 over infinity, so the limit would be 0. So it is the same for sequences. So all sequences of this form are convergent. So for example, the sequence 1 over n is convergent. The sequence 1 over n square is convergent. The sequence 1 over n to the power half is convergent. The sequence 1 over n to the power 0.1 is convergent. Whenever r in all of these sequences is greater than 0. So all of these sequences converges to what? To 0, because their limit would be 0. But if r is negative, then you will have something like this. But then this would be n, and it will not be convergent. Some exercises determine whether the sequence converges or diverges. If it converges, find the limits. Arc tan inverse of ln n. Well, if I want to work with f of x with a function, so what would be the function? The function would be tan inverse of ln x. So you can see that f of n, when I replace x by n, I get an. I get the sequence an, isn't it? So it would be tan inverse ln n. So if this is the case, if you are using the function in which f of n equals an, find the limit of the function and it would be the limit of the sequence. So let us find the limit. of tan inverse ln x when x goes to infinity. Well, ln infinity is infinity because ln, this is the graph of ln. So ln infinity, when x approaches infinity, ln also approaches infinity. So I will have tan inverse of infinity. And you know the graph of tan inverse. If x approaches infinity, it approaches this line. This line is a horizontal asymptote. So when x approaches infinity, tan inverse approaches pi over 2. So in fact, the limit of tan inverse ln x is pi over 2. So this means that the limit when n goes to infinity of tan inverse ln n is also pi over 2. And this means the sequence is convergent and it converges to pi over 2. Another sequence called squeeze theorems for sequences. And it's a squeeze, we call it squeeze because a sequence Bn here is between two sequences, bounded above by the sequence Cn and bounded below by the sequence An. All the terms of Bn are between An and Cn for each n greater than n0. N0 is some n after 10 terms, 100 terms, whatever. Bn would be between these two sequences. Now, if I find that the limit of An when n approaches infinity is equal to the limit of Cn when n approaches infinity is equal to L, then the squeeze theorem will say that, okay, so the limit of Bn has to be also L because Bn is in the middle between them. So that's the squeeze theorem for sequences. We use it to find the limit of sequences like this, determine whether the sequence converges or diverges. When we have cosine or sine, we know that cosine is always between -1 and 1. Also sine between -1 and 1. But here we have cosine square. Well, cosine square, because it's always positive, would be between 0 and 1. Because cosine square is always positive, it's always greater than 0. So I have cosine square n between 0 and 1. Now, I want to use the squeeze theorem. So I want to put an, the sequence an, this sequence, between two known sequence to me. So what if I divide by 2 to the power n? So 0 over 2 to the power n less than or equal to cosine square n over 2 to the power n less than or equal to 1 over 2 to the power n. Well, 0 over 2 to the power n is just what? Just 0. So now this sequence an is between two sequences, 0 and 1 over 2 to the power n. So limit of 0 when n approaches infinity is 0. And the limit of 1 over 2n, 2 to the power n, when n approaches infinity is also 0 because this is 1 over 2 to the power n, okay? Or it is, 1 over 2 to the power n. Or you can say because infinity, 2 to the power infinity is infinity, 1 over infinity is 0, so the limit is 0. So by squeeze theorem, the limit of cosine square n over 2 to the power n when n goes to infinity is also equal to 0. And this is what the squeeze theorem says. This is another example. Cosine n pi is always between -1 and 1. If I divide by 2 to the power n, Notice that this is 2 to the power negative n. So I can write it cosine pi n over 2 to the power n. So it would be this sequence. Now, what is the limit of negative 1 over 2 to the power n when n approaches infinity? 2 to the power infinity, negative 1 over infinity is 0. And also limit 1 over 2 to the power n when n approaches infinity is 0. So by squeeze theorem, okay, limit of cosine n pi over 2 to the power n when n approaches infinity is also 0. Another example about the squeeze theorem. Look to this sequence, n factorial over n to the power n. Let us understand the nth term here. What is n factorial? We said n factorial is n times n minus 1 times n minus 2 up to 3 to 1. And n factorial is n times n times n times n, n to the power n, sorry. How many times? N times. So here we have n times n numbers multiplied by each other. And here 1, 2, 3 up to n times. N numbers multiplied by each other. Let me write them like this: n over n times n minus 1 over n times n minus 2 over n up to 3 over n, 2 over n, 1 over n. Now notice that this number is 1. This number n minus 1 over n, like 6 over 7, this number is less than 1. This number is less than 1. So I can say that this sequence is less than or equal, not equal because it's less than in fact, is less than 1 over n, the last term. All of these terms are less than 1. So if you multiply this by a number less than 1, then it would be greater than an. So n factorial over n to the power n is less than 1 over n. And it's of course greater than 0 because it's positive. And limit 1 over n when n approaches infinity is 0. And limit 0 when n approaches infinity is 0. So by squeeze theorem, limit of n factorial over n to the power n when n approaches infinity is also 0. These are 3 examples about the squeeze theorem. I stop here and continue later.